Right. So just to reiterate the practical, I will. So let me first state chance identity, and then I will come back to the practical computation. So chance identity. Chance identity tells you that if you have two paths in so x and y in CP for P1 and 2, then the signature of the concatenation, so of the path concatenation, is equal to the tensor product of the two signatures. Okay. So this is quite deep, right? Because it means that the signature is almost like a functor, right? I mean, it maps paths equipped with concatenation of two curves, right? This is literally, you have x, and then you're concatenating x with y. You map path with this product concatenation to tensors with the tensor product, right? So that's signature of x times signature of y. So so the proof of this statement is quite easy. I mean, it's essentially so the proof, you prove it by so for p equals 1, you can use Fubini's theorem, and then plus density argument, that the same density argument that we have seen before for higher p's. So okay, so the practical consequence of this, or let me erase this, is not. The practical consequence of this is efficient computations, right? As I tried to mention before. So let me just give you a practical example. So suppose that you're a practitioner and you have a time series, right? A time series that is made of points, time-stamped observations like T1, x1, T2, x2, Tn, xn, where xi's are the dimensional vectors, right? Rd. So one way of seeing this time series, this discrete sequence of data as a path, is interpolating linearly, right? So you have these points that you observe over time, and you just draw straight lines in between. Okay, and then you consider, let me call x at 1 the linear path that connects the first two observations, x at 2 the linear path that connects the second and third observations, and so on. Okay, and let's suppose that we want to compute the signature of this time series, of this linearly interpolated time series. Well, we can combine the chance identity with the previous statement in this way. So the signature of the interpolated time series x by chance identity is going to be equal to the signature of the first linear piece x1, tensor product, the signature of the second linear piece x hat 2, ... Sx hat n. Okay, so that's by Chen. And then, thanks to the previous statement that told us that the signature of a linear path is just the exponential of its increment, this gives that the signature is just the tensor exponential of the linear pieces. Where delta, it just means the increment from the end minus the beginning, okay? So is that, I don't know who asked me the question. That's, okay. And yeah, and so here during the break, so these are names of Python libraries that you can find out in the wild to compute signatures. So there are, so the one that Terry mentioned during his talk is RAFPy, is somehow the most modern one. However, so you can, it has functionalities that go beyond computing signatures. You can do many different things. It is not very compatible. I don't know if Terry is connected or not, but well, anyway, it's not super compatible with yet. I know that that's the effort is being done to make it compatible, but it's not yet compatible with deep learning libraries like PyTorch and JAX. So, if you want to use the signature as a layer within a neural network, yeah, this is not ready yet. So if that's your need, then maybe these two libraries are more appropriate. Signax is actually currently actively maintained by a mathematician in Korea. So it's a very lightweight, nice modern library based on JAX, and signature is not maintained anymore, and this PyTorch based. Yes. Yeah.
Hello. Yeah.
Yeah.
I have a question. So now you have this nice way to compute. Have a piecewise linear, essentially, path, right?
Yeah.
Now, this is based on the extension of this discrete time series into, and that is essentially sampling frequency dependent. So if you want to characterize somehow the signature of the path that is behind this sampling, right? How far is this signature from this ideal signature that you would obtain if you would go in continuous time, for example? That will give you some kind of robustness of this with respect to the sampling frequency, right?
Yes. I think the question, it's not too much about this. In that case, if you're interested in measuring the error that you make by interpolating with respect to a continuous underlying path, it's more like what's the error at the level of the path that the interpolation makes, right? So what, depending on what kind of topology do you have on path space, you can somehow separate out the problem into computing the distance between the interpolation of the path and the underlying continuous path. And that, essentially, that error will be then fed into the signature.
Because usually you have, you don't do these things for fun, right? So you have something in mind to compute. It may not be the signature itself.
Right.
So in some sense, you're trying to propagate the error made on this level to the final level. So you're not really trying to put kind of distance on the signatures, and that would be far-fetched, right? It's efficient somehow.
Yeah.
So have you seen this thing of connecting, say, final goals, essentially, errors that one does in signatures? Maybe very vague
yes.
goals, right? But you have something to show.
No, yes. I mean, there are some statements that try to, but it depends in which community. Like, for example, if you're in, yourself in the stochastic numerics community, the input path that you would deal with is a Brownian path. Okay, and the Brownian path, in principle, it can be queried at an arbitrary resolution, right? It doesn't come as as at a fixed with a fixed sampling frequency, but it's really can be queried at an arbitrary resolution. So in that case, also the signature can be computed at an arbitrary resolution. And using chance identity, you can actually, for example, use dyadic partitioning to compute signatures over smaller intervals, and then concatenating them, right? Then taking the product to compute the signature on a bigger interval, right? So in that case, because you can query the path at an arbitrary resolution, in the case of Brownian motion, you can also query the signature at an arbitrary resolution. So in your SD solver, you will use the second level of the signature, for example, at the given resolution to build a second order numerical scheme for SDs.
And in that respect, times when you sample.
Yeah. Yeah, in data science, which is where the input signal is not Brownian a priori. I mean, it's just data that comes at the irregular sampled. There is no requirement that T1 is equidistant from T2, which is equidistant from, yeah.
That I understand, but it was in the other direction, right? I mean, would in some senses make sense not to sample uniform.
For what's the objective?
That, for example, the process is not passed in certain regions.
The sampling frequency at which is more convenient to sample the path, it's I guess it's expert knowledge of the practitioners that but then the signature is applicable in in their regularly sampled case. Yes. Yeah. I don't know if that answers your question, but right. So okay, so that's computations. And so then the last property, which algebraic property, is the shuffle identity. Okay, so the shuffle identity is okay. It's a little bit tricky to introduce, but I'll try my best. So so I was telling at the beginning that this vector space extended tensor algebra T of B. Well, let's look at just this one, just the tensor algebra. TV can be equipped with a product and can be turned into an algebra, right? A non-commutative algebra. And that product was the tensor product. So this is a non-commutative algebra. Now, it turns out that there are other products that can be, that this algebra can be endowed with. And another one is what is called the shuffle product. So it's denoted in this way. And so the shuffle product has a precise recursive definition that I don't want to give you because it's not very interesting for the purpose of this course. It's much easier to think of define the shuffle product on basis elements, okay? So, you take just two words, orally, you take two words, and the shuffle two words of length. So let's suppose that I have a word of length R and a word of length S. Now the shuffle product of these two words will be a word, will be a linear combination. So a sum of how many? Of R plus S, choose S words of length R plus S. Okay, and so if you take two words of the shuffle product will be a sum of these many words of length R plus S, and the words that appear in this sum are obtained by essentially interleaving the two separate words one with the other without changing the order of the letters, right? So I'm not going to write down the specific definition, but I will give you some examples. So if you take two words, like for example, the word E1, and you shuffle it with the word E2, then you will get E1 tensor E2 plus E2 tensor E1, right? So you would just put, interleave them as you're shuffling two decks of cards in this way. If you take two words of the form E1 tensor E2, this is one word of length 2, and you shuffle it with another word. Let's take E2 again. Now this will give you what? This will give you E1 tensor E1, E2, sorry, tensor E2. That's just putting them together without changing the order. But then I can put the E2 inside the letters E1, E2. So I will get I will get again E1 times E2 times E2. So this is twice this. And then I will get E2 interleaved at the very beginning of the previous word. So I will get E2 tensor E1 tensor E2. Okay, and so on. Of course, this space is the space spanned by all possible words. So if I know if I define a product on basis elements, I know how to define a product on the whole space. Okay. So this is the shuffled product. So with this product, here is what happens. You get something called the shuffle identity that I will use now. So if you take let I be a multi-index. Okay, so let's index words by multi-indices, right? So this is I1 dot ij. So this is a multi-index that will index a word of length j, and let j be another multi-index. Sorry, let's say IP. So this is a word of length p, and j is a word of length q. Okay, and so then the corresponding basis elements will be, so EI will be just EI1 tensor EIP, and similar for EJ. Then you have this lemma is that if I take the ith element of the signature, so EI signature of X, this means the ith coefficient of the signature corresponding to this multi-index. And I take the pointwise, this is a scalar, right? So this is a pointwise multiplication with the EJ, right? EJ element of the signature of X, of the same path X. This is the same as taking the elements obtained by shuffling EI with EJ. This is another element. This is a linear combination of words that then I can contract against the signature. Okay. So, sorry, this should be star, okay, because these are in the dual space. So this EI star is just EI1 star, EIP star, and similar for EJ. Okay, so this is the statement. So the pointwise multiplication of two linear functionals acting on the signature, or two words acting on the signature, is equal to the shuffled product of the two linear functionals acting on the signature. Okay. Right. Yes. What's next? Sorry. Just. Yeah, an example. Yeah, okay. So the proof is it's not very complicated. You do a double induction. Okay? You do a double induction on the levels, on the length of the two words. Yes. Can I? I'm not sure I can, but I can try. I can try. I think so. You know, so the proof of this is just a double induction on the length of I and j. Now, so let me give you a simple interpretation. So if you take this, if you apply this this part, right? If you take this example here, then and you apply to this shuffle identity, then what you have? You have that E1 star applied to the signature of X times E2 star applied to the signature of X. If I spell this out, this is just the integral. So this is just the integral of dx coordinate 1 between A and B, say, times the integral of dx E2, right? And with this is just the increment, right? So this is xb minus xa, first coordinate, sorry, times xb minus xa, second coordinate. And then the other part, so this part coming from the shuffle identity, it is telling us that this is equal to E1, E2 star applied to the signature of X plus E2, E1 star applied to the signature of X. And now, if I spell out in terms of iterated integrals what these two terms are, well, this is just going to be the integral of AB between AB of, I guess, X, X1 t minus XA dx2 t, and this is plus the integral of AB, the other one, x2 t minus x2a dx1 t. Okay? And so now, if you look at this equals to this is just integration by parts, classical integration by parts. So this shuffle identity here is just a generalization of the integration by parts to higher order integrals. Okay. Okay. You really want higher order? Yeah, but still, yeah. Yeah, things can go wrong, but yes. So you want things like E1 tensor E2, and then you want me to shuffle it with something like E3 tensor E4. Is this really what you want?
Yeah, but so usually the recursion is you have if E1 and E3 are also tensors, then this is just shuffle of everything and then E4 to the right.
Yeah, there is a recursive definition of shuffle, but I don't want to write it down because it's I think it's this is a more okay. Yes, there is a thanks, but no.
Okay.
Yeah, this is not a definition, right? It's more like intuition. Yes.
Yeah. I mean, if you have the recursion, but
yeah. Okay. Yes. Okay. So this. Okay. So to recap, what do we have? We have sampling invariance of the signature, so that's good for removing this reparameterization group. We have factorial decay that allows to be sure not to kill too much information. We have uniqueness, at least on some types of paths, time-augmented paths. We have chance identity that allows to do efficient computations on a computer. And we have this shuffle identity, which generalizes integration by parts. Okay, these are the 5 properties that we have seen so far. And now what we can try to do is to, let me just here, get to the meat of the, do I want to get to the, so let me just, what do I want to say? Yeah, okay, so this I will skip for now. I will come back to it later. Right, so so the next part that I wanted to talk about are unparameterized paths. Unparameterized paths, where I will try to put together all these properties in a coherent way and explain one of the main reasons why we want to use signatures in machine learning. So, we've already seen that if I reparameterize one path by a lambda, I don't change the signature. Okay, so, and we have already seen that if we haven't seen it, but it's sort of obvious that if you shift the path by a constant, you don't change the signature either. So the signature doesn't see the initial point of the path either. So in other words, if we want to ensure that the signature is a faithful map on a path, we need to somehow remove this redundancy, these invariances, okay? There are various ways to remove them. One way is the easy way, which is the following. So you take your path space, so CP, smooth path space, right? So 1, P, S, and 2. And then you define an equivalence relation on this path space, which goes as follows: X is equivalent to Y if and only if signature of X is equal to the signature of Y. That's it. So that's an easy way to solve my problem. Now there is a theorem, a deep theorem, series of theorems by Lyons and Humbly-Lyons. Humbly-Lyons in 2010 in the Annals of Maths, that essentially recognize what are the transformations at the level of the paths that ensure this equivalence. Okay, we have already two examples that I've mentioned before: reparameterization and translations. What they've done is that they've identified a more general class of reparameterizations that I will not discuss in this talk or in this mini course that ensures this equivalence. And in pictures, just pictures, so if you have a path like this, what you can have is that you can have some tree-like excursions. So you go along your path, and then at some point you go away, you go up, for example, and then you come back, and then you go like this, and then you come back, and then you go like this, and then you come back, then you come back here, then here, and then maybe you have another excursion here, tuck, tuck, and then you come back, and then you continue, right? So these are sort of tree-like, called tree-like excursions. It can be thought of as a generalized version of reparameterizations that you can add to your paths to make something like this. And it turns out that these are all the type of modifications of your path that you can do to ensure that the signatures are equal. Okay, so two paths. So this equivalence is equivalent, okay, to saying that the two paths are tree-like reparameterizations of each other. Okay, and this is a deep theorem that I'm not going to discuss, but we will just care in this course about this definition of the equivalence relation. But just to let you know that there is a very nice paper, well, important paper. I don't know how nice it is, but that does this at the level geometrically at the level of the paths. Okay, right. But yeah. So for now, we will take this definition, and then okay. So the space of unparameterized paths. So definition. So curly CP. So the space of unparameterized paths of finite p variation is simply going to be defined as the space of paths of finite p variation modulo this equivalence relation. Okay, but the equivalence classes of paths that share the same signature. Okay, so yeah, so this is going to be an important part of the next statement, which is an important statement as I anticipated. So this is so yesterday Jack gave an example of a universal approximation theorem. I will give you a different one today. So universal approximation. So in words, what I'm about to write is that if you have a function that acts on unparameterized paths, and this function is at least continuous, and the space of paths that you're acting on is at least compact, then you can approximate uniformly well this function as a linear functional on the signature of your paths. Okay, so linear functional on the signature form a universal set of approximators for functions on paths. Maybe you know, surely all of you are familiar with the equivalent statement at the level of polynomials. Any continuous function on a compact set on RD is approximated uniformly by a polynomial. Maybe less of you are familiar with the neural networks approximation theorem, which is very similar, but instead of using polynomials, you use neural nets with non-polynomial activation functions, but that's a detail. Here is another type of universal approximation where the functions that of interest are functions on paths. Okay, so functions on time series, if you want, if you're more practically minded. Right. So the statement goes as follows. So we have f to be a functions from unparameterized paths to R. Okay, which is at least continuous. Okay, so here just continuous. We might open a very big parenthesis, because what does it mean to be continuous on equivalence classes? Okay, so you need to have a topology on that space, and you need to pick it carefully. But we will. So okay, so here you need a topology on equivalence classes, and I will point out the recent paper by Tom Cass and Will Turner, 23, where they discuss different choices of topologies on unparameterized paths. To have this function, then you give you consider a compact set, so K, of unparameterized paths. Again, compact in which topology, but in the same one that F is continuous. So that's the second ingredient. And then essentially what you can show is that you can approximate this function uniformly by a linear functional on the signature, right? So there exists, if you take the uniform norm of F minus, for all epsilon greater than 0, there exists, I didn't want to write it down fully, but okay. There exists a linear functional L in the dual of the tensor algebra, such that the uniform norm of F minus L composed with S, and this is a uniform norm over a compact set K, is less than epsilon. Okay, so that's what a universal approximation looks like. Okay, so if for any function is continuous on a compact set, I can find a linear functional that acts on the signature such that this linear functional is uniformly close to F in K with an arbitrary precision. Okay, that's it. Another way of saying this, equivalent way, is that linear functional on the signature. So let's take A and A to be the space of linear functional acting on the signature. Okay, where L is a linear functional. And this is seen as a function on unparameterized paths, right? So this is a subset of CP. Sorry, no, that's wrong. This is a subset of continuous functions from CP to R. Okay, so you have this set of functions on paths. so an alternative way of stating this theorem is that A bar infinity, infinity, restricted to K, equals, I think, or at least contains, but I think it's equal, T K. Okay, so the space of linear functionals on the signature restricted to a compact set of unparameterized paths is dense in the space of continuous functions on the compact set with respect to the uniform norm. Okay. Yes.
So this is this. Yes, can I view that as what? As infinite dimensional PCA, where each factor is an element of the signature. Then you some of them basically.
Sorry?
So I have a function.
Yeah.
I view each element of the signature, the factor. I have a linear map, takes them all, set up those as I want.
Yeah. Yeah. So a picture to retain this is that, so if you have your unparameterized paths here, and you have your function that is a real valued function, f, that you want to learn, or you want to approximate, this might be nonlinear, nasty, complex function. What you can do is that you can lift your path space with the signature to T of B, and then you can find the linear function, so L linear, that close the graph. Right?
Main point is
that exactly. The main point is that linear. And this is a precursor to what the second part of the course will be on kernel methods, and this is very much in line with that's the feature map, exactly. Yes.
With linear.
Yeah, it's linear. Yes, it's exactly like polynomials, right? You can you have a continuous. Yeah, but essentially the signature plays exactly the same role as polynomials, but for paths, right? The iterated integrals are exactly like monomials, and then linear combination of iterated integrals are polynomials. Yeah, that's the analogy. Yeah, yeah.
Maybe a comment to Jack's question, because I think the main difference to CA and this is this approximation result is strictly pathwise. PCA has a distribution in the background, right? Yeah.
Yes.
I was wondering when. So basically, there is no. So does this say that there's finite topology? Because basically, I think about this Gaussian CP, in some sense, one-to-one with the signature. All elements are parameterization. If I would see, I mean, basically, if I had a topology on the signature space, I could write down another map instead of F that maps directly from the signature space to R, which is in some sense same as F. Then that is continuous. If I had a topology signature space, then I would just find out, okay, it has to be linear anyway. So basically, I don't need a topology or any sense of continuity. Okay. Look at mappings directly from the signature space to, say, R in this set.
Well, to talk about continuous functions in the first place without talking about signatures You sort of need a topology there, right?
Yes, there, of course, yes.
So that's why independently on how the signature is, actually you also need, this topology has several constraints. For example, the signature map as a map from paths to the tensor algebra needs to be continuous with respect to this topology, actually, for this to work. There are some details that I'm not telling you, but actually the choice of topology is not a very exciting thing, I would say, to think about, but it's quite, so, you know, this type of statements have been stated in several work, you know, in the past 5-10 years without making too precise this the choice of topology, but actually it turns out that you really need to be careful about that. Otherwise, the statement is actually not true. So, for example, if you work with paths, that's clearly not true, and I will explain now why that's the case, because the proof is quite simple now that you have all the properties in front of you. But yeah, no, I think the choice of topology is actually quite crucial.
What I was wondering actually, is there motivation at all to, I mean, right now it's an algebraic object, but you could, I mean, this is actually related to Raoul's question, because he was asking about approximations of signatures. In that sense, I would ask myself, is there a way of finding a meaningful metric on the space of signatures? And in that sense, you will also define a topology.
Yeah. I mean, you have different ways. Yes, if you can start with you can start with norms on the tensor algebra, right? For example, and you can pull it back to define a norm on path space. You can start with the norm on path space with the topology on p variation, like p variation, for example, and you can massage it to make it into a norm of the tensor algebra. I mean, yeah, you can go back and forth between the two, and there are different choices. There is no canonical choices.
Okay.
But there are different choices.
So basically, there is no induced canonical topology that comes from the topology on the path space. I mean, if you have a topology on CP, probably not. If I understand you right, you will probably not get a canonical topology on.
Well, if you fix a topology on CP, yes, but there is no canonical topology on unparameterized paths, so curly CP, that for which this theorem holds. There are many choices, at least 3. I don't know. That's many, but yeah. Yeah, no problem. Okay, so here's the proof, or a sketch of the proof. So the proof is entirely based on verify the assumptions of the Stone-Weierstrass theorem. Okay? Stone theorem, which are the following, right? So the Stone-Weierstrass theorem tells you that, so if you have an algebra, right? If you have an algebra of functions A, that is a subalgebra, so restricted to a compact set K, which is a subalgebra of the space of functions that you care about. So in this case, it's continuous functions on K. So you need to have 3 things, right? So A, first of all, that A is an algebra, right? So A is a subalgebra. So the algebra here is with respect to pointwise multiplication, right? So that's the algebra structure. The first thing is that A needs to be a subalgebra. I'll leave some space so that I can feed it with the details. You also need that A contains the constant functions. And then you need A to separates points. And so what this means, separating points, is that if I have 2 points X and y in k that are different, so x different than y both in k, then this implies that I can always find the function f in A such that f of x is different than f of y. Okay, so if you have if the subalgebra of functionals that the candidate that you have in mind satisfies these three assumptions, then this theorem, the Stone-Weierstrass theorem, tells you that A sub k tells you what we need, right? A sub k, the closure in L infinity is equal to ck. Okay, so all we need to do is to verify that our candidate, this one, satisfies these properties. Okay. Okay, so why is this a subalgebra? Well, because of the shuffle identity, right? So shuffle identity. You know, I take two linear functionals and I multiply them pointwise, two linear functional on the signature of a path, and then multiply them pointwise. I get another linear functional that acts on the signature, which is the shuffle of the two. Okay, so it is a subalgebra of the algebra of continuous functions. It contains the constant functions because the signature starts with 1, right? So the signature starts with 1, so I can always take the projection of the signature. I can always take this function, so lambda pi 0. So this pi 0 is the projection of the tensor algebra to its first level, and then I can eat the signature of no matter what path, so x s dot, and this gives me lambda, right? Because the projection to the 0th level is 1, and so that's just lambda. And so clearly, among all these linear functionals, I have the ones that are constant in the path, in the input path x. And then the fact that the A separates the points come from uniqueness, right? It comes exactly from the fact that we are working on unparameterized paths, right? So, you know, if I have two paths that are different, I can always find a linear functional that on the signature that keeps them different because we have we are working on equivalence classes. Otherwise, this would not be true. Okay. Yeah, that's it. That's the proof. It's a simple application of the, well, simple once you know all the rest. Are there any questions on this? Yes. Yeah. Identify lots of paths. Yeah, so that's a good that's a very good point, because you're saying in practice, how can I guarantee that exactly, how can I guarantee that I'm in a setting where this theorem holds? So an alternative, so if instead of considering unparameterized paths, I consider paths, just classical paths, then where would this theorem fail? Well, it would fail at, it would not fail at the level of the subalgebra, right? Because the shuffle identity still holds. It would not fail at the level of the constant because that still holds. It would fail at the level of separating points, right? Yeah. Let's say. Yeah, but I'm getting to your point. So yeah, so an alternative, so the separating points property essentially relies on this, right? But we've already seen that, so it relies on the faithfulness or the uniqueness of the path with its signature, right? So another way of ensuring uniqueness, as we've seen, half an hour ago, is to add a monotone coordinate, right? So if you add, so if you're interested in functions that act on paths with one monotone coordinate, so with time, then essentially this theorem holds without all this unparameterized business, right? You can directly reprove it. Essentially, the rest of the proof is the same, and then the point separation property holds for the same reason as it holds now, right? So an alternative version of this theorem would be, if you want to approximate a function on a time-augmented paths, you can do this procedure, and the theorem would still hold. Yes. I don't know. Is this what you? Yes. Well, adding time is sometimes not a good idea, right? That's so I don't have a full answer. Yeah, but for example, if you want to encode this invariance reparameterizations, right? Like you're drawing digits, right? Then it's not clear that adding time is a good idea, right? Because you really want to capture the geometric shape of the curve without looking at the reparameterization. In that case, it's not a good idea to add time, right? For example. But in finance, for example, I think it's quite clear that adding time is a good idea. But yeah, I don't have a full answer for what in practice how to ensure unparameterized paths without adding time. Okay, so in the next 5 minutes before getting to part 2, I just wanted to have a simple consequence. So this is more no, actually I have more to say. So a consequence of the shuffle identity, which I think it's an important property to keep in mind. So we'll do this through a series of it's a couple of results. So the first result, which is this one, so lemma. So if you give yourself, so consider n, so h1 ... hn to be n distinct signatures. So n distinct signatures. Then what you can prove is that there exist. Okay, so let me just skip one result and give you the one that we need. Then what you can prove is that these signatures are independent. Hn are linearly independent. Okay, so in the sense of linear independence, right? So yeah, so how do you prove this? I don't think we have time to go into the details, but essentially what you can prove is that you can find the linear functional that is one on the, without loss of generality, it is one on the first signature and it's zero everywhere else. Okay, and then you use that fact you can construct that linear function in that way. And then you use that fact to show linear independence. Okay, and the linear function it can be constructed using the the Anbanach theorem and then the shuffle identity. So the shuffle identity is crucial to construct a linear function. So there exists L such that L h1 is 1 and L hi is 0. Okay. You can construct this using the shuffle identity, and then you can use this construction to prove the linear independence. It's just a simple consequence. Now, if you, yes. Just, I mean, there is at least one entry that is not equal. Yeah, they can be different, yes. These are just signatures, yes. They're signatures of some paths. Yeah. Yeah. It's different, yes. Yeah, I think that would work. Yeah, yeah, yeah. So they have this special linear independence structure, and so this is actually useful to prove the following theorem. And this theorem holds in much greater generality, which goes as follows. So if you have two now. I'll do a little bit of probability. So if you have two probability measures, so H, so let's take one, H, a probability measure on, okay, so supported on a discrete collection of distinct signatures. Okay, so you have a finite collection of distinct signatures. Yes. So if you sum two signatures, you want to get a signature. Yes, that's not necessarily related to this lemma, but yeah. 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 No. Yeah. No. Well, actually, you can prove that a generic tensor in the tensor algebra, which is a bigger space, it can be always written as a linear combination of signatures. So actually, signatures span the space. So actually, because they're linearly independent, they're essentially a basis for tensors. But they're not a canonical base. They're not canonical at all. But but you can represent any tensor. I don't know if it's a good idea to do that, but you can represent any tensor in this generalized way of thinking about tensors as linear combinations of signatures of paths, actually. Yeah. So, I mean, it's very easy to say, because if you add two signatures, you get at the 0th level, you get 2, which is already a killing thing for signatures, right? So yeah, Right. Okay. So the theorem says that if you have a discretely supported probability measure on signatures, right, then its expectation characterizes its law. Then the expectation of H characterizes the law of law of H. So what do I mean by characterizing the law? I mean that if you have two such probability measures, so H and P, and you take expectation of both, then this is equivalent to their laws being equal. This is quite deep, right? Because I mean, it's not deep because you have, in this case, you have discretely supported probability measures, right? So I mean, the proof, it will be simple as I'll show, but this result holds in much more general settings where, you know, if you have two probability measures supported on path space, okay, with some assumptions that needs to be satisfied, then the expected signature, so the expectation of their signatures, characterizes their laws. So the expected signature is a powerful object that can be used to represent stochastic processes, essentially. Okay. This is okay. So that statement needs a lot of refinement and a lot of assumptions and blah 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 blah. And there are many nice theorems and results that have been obtained recently. For example, so I'll refer to a generalization of this statement is in Cheverev and Oberhauser. Actually, this is in the Journal of Machine Learning Research, 22, I think. The generalization of these statements for stochastic processes. But okay, in our setting, this is easier. So you know, the proof of this is essentially the fact that you know what it, so expect. So if you suppose, so okay, mu. Let's take mu h, you know, to be just a linear combination I equals 1 to m of alpha I delta h I. Right, so this is a probability measure supported on a discrete set of distinct signatures. That's important, and similarly for mu p, j equals 1 to n beta j delta pj, and then you know it's clear that if you have equality of expectations, what happens is that you have equality of these two sets, well, these two linear combinations, sorry, alpha I, hi, beta j, pj. And now, because we said that two distinct signatures are linearly independent, it must be that this is equivalent to these two sets, so the sets alpha I, hi, you know, for I from 1 to m, and the set beta j, pj, j equals 1 to n, these two sets of tuples being equal, right, because of the linear independence. And now these two sets are equal if and only if the two measures are equal. Okay, so this statement in the statement here, which is really, I think for stochastic in stochastic analysis is a really powerful statement, is not this one because this is simplified, but in this simplified setting, it can be proved with these. Right. So I think we can. Yeah. Okay. So there is. So I have an interlude on neural control differential equations, which. So if you don't mind, I will. I will keep for at the very end. So I will come back to neural control differential equations later, because yeah, it will break a little bit the story. So I will come back to it later on. So I think this is good point to go to part 2. So part 2 is signature kernels. Right. So Jack already mentioned something about signature kernels yesterday, and Christian, of course, mentioned something about RKHSs, a lot about RKHSs yesterday. Right. So so kernels are a class of mathematical objects that are at the core of several machine learning algorithms that are more or less mainstream nowadays, right? So for example, I'm sure that many of you heard about support vector machines that actually Jack gave an example of, but things like, from non-parametric hypothesis testing to, Gaussian process, Bayesian inference with the Gaussian processes, to generative models, so how to design a discriminator to train your GAN or other type of generative models, are all based on kernels. So, and even more recently, there is a very hot topic in machine learning in deep learning, is to also recognize that if you take your, a neural network and you look at scaling limits of a neural network, so you let the width or the depth or both go to infinity, then in the end you get, usually a Gaussian process or something more complicated with a covariance structure that is given by a kernel, right? A kernel on the space that you care about. So kernels can be also interpreted as infinitely wide neural networks, and I will give you at the end tomorrow, at the end of the course, an example on how that would work in the case of paths. But so kernels are sort of mainstream and everywhere, and although people not necessarily familiar with them. And so in its most basic form, the idea of a kernel is very similar to the idea that I gave before of a lift, right? So you might, you have your data that lives on a space X, and the idea of a kernel is that of lifting points. So a kernel K lifts your points into a Hilbert space H, which is often infinite dimensional, but in such a way that essentially, if you have, for example, the example that Jack gave yesterday, if you have, some points that can be separated by a nonlinear relationship. So in this case, I don't know how you do colors here, but here, let's try. In this case, a separating hyperplane, well, it's not a hyperplane here, but the separating space for these two clouds of points would be a nonlinear function, right? A circle. But if, for example, you take a polynomial kernel that simply squares and adds your points, you will transform this relation, this nonlinear, in this case, quadratic relation, into a linear one on H. Okay, so that's the point of kernel methods, is to lift your space to a Hilbert space with the intention of linearizing possibly nonlinear relations on the underlying data space. That's the motivation. Okay. No. Right. So in line with the theme of this course, for me, X, the space where the data lives, would be paths. Okay? Paths. Well, let's be more precise. CP paths. Again, with P between 1 and 2. Right. And okay, so the goal is to now to give you an idea of how to do this using signature type techniques, as we've done so far. There anything I should say before? No, that's it. Okay, so Hilbert space. Okay, so we need a Hilbert space, so at least we need an inner product. Okay, so recall this this tensor algebra. So let's go back to the extended tensor algebra T of V. Okay, well, let's see. Let's start with V. So let's start with an inner product. So let this be an inner product on V. So I can add a little bit more structure on the base space of my paths by equipping it with an inner product. Okay, so Euclidean inner product if you are in RD, or something more fancy if you want. Now, if you have an inner product on V, it's, sorry? V. Here it's I'm considering paths, in V. Yeah, I'm not being very careful at all with the notation, but these are really functions from 0, 1 with values in V of bounded p variation. H will come in 5 minutes. Yeah. But the base where the data lives is path space with values in V. Now I'm about to construct the H. Yeah. Yeah. So V for now is a vector space, right? So now I will add a bit more structure to first make it an inner product space by adding an inner product. Then what I will do is that I will say, okay, now if I have an inner product on V, how can I construct an inner product on V tensor power K? Okay, well, you can use an Hilbert-Schmidt type inner product to simply say that this is just equal to U1 inner product to V1 in V times UK, UK VK inner product in V, right? So it's so to have an inner product in V tensor K, it's easy. And now, if you have an inner product in V tensor K, you can have an inner product in T of V in the tensor algebra over V here there are different choices. Okay, so here there are different choices. The simplest choice is this one. So you just take the infinite sum 0, I guess, infinity of U I VI in, let me put K here, K in V tensor power K. Okay, so that's one way of defining an inner product on T of V. So let me remove this T of V so that we don't carry it around all the time. And now there is somehow a more general class, which is by no means the only choice, but I think it's an interesting class of inner products, which are called weighted inner products. So they're weighted by a function phi that acts, here like this, that acts, so this is phi k U k VK. Oh God, okay, V is used too many times. Sorry about this. To AP. AK, EK. Okay. Where phi is just a function from the natural numbers with 0 into, let's say, R plus. Okay, it's a positive weight. Okay, so and this is a weight that rescales each level of this tensor algebra in different ways, right? So it's an arbitrary function that we can put there. Okay. Okay. So then T of V equipped with this inner product is an inner product space. And now what I can do is that I can take the completion. So I can take T of V, and I can complete this vector space with respect to this inner product to get a Hilbert space, T phi V. So T phi V is just the completion of T of V with respect to this inner product. So the completion is the set of equivalence. Set of equivalence classes of Cauchy sequences that have the same limit in this space. Okay, so here is a Hilbert space. So this is Hilbert. Right. Okay, so now, of course, we have been talking about signatures. So at the very least, what we would like to ensure is that signatures live in this space, right? Are elements of this space. And so just as a reminder, so we have the smallest space is TV with only one bracket. The signatures don't belong to this space because this space is too small. This is included in this space, T phi of V. And now this space is included in the big one, T double bracket V. So we know that the signatures live in this one, right? So now what we would like to do is that we would like to ensure that this middle space, T phi of V, is big enough to contain signatures. And so then we can take inner products. And that's quite clear. Okay, so a simple condition is this. So recall that by the factorial decay, we have that the signature, the kth level signature of let me take the full signature with respect to this norm. What is this? This is just the sum. By definition, this is the sum I equals 0 to infinity of phi I. But I guess this is less or equal than this. And then you have the signature of X at level I over V tensor I. Okay? But now by the factorial decay, we know that this is less or equal than the sum I equals 0 to infinity of phi I, the one variation of the path x1. Hold on, could be some squares around. Yeah, this is a square because this is the norm. It's the inner product. Yes, this is a square. So this is 2 times I divided by I factorial squared. So this was by the factorial decay. Sorry? Here? Here. Yes, thanks. Yes, that's right. Thank you. Right, and so here, okay, so for this right-hand side to be finite, what, a condition on phi is the following. So condition, let me call this condition star, is that for any positive constant, this series is summable. Okay, I equals 0 to infinity by I c to the power I divided by I factorial squared is finite. Okay, so if phi has this property, So if phi is such that this series is summable, then the signature will live in this Hilbert space. Okay? So if star is satisfied, so the image of the space of paths by the signature will live in T phi of V, will be included. Okay? Right, so now that I have, so if I don't say otherwise, this I will not say, let's consider a phi that satisfies star, like if phi will automatically satisfy star, and I will give some examples. So one simple example for phi satisfying star is taking phi to be constant. Okay. This because the factorial always win. But there are other choices. Right, so, okay, so then if we have this, we can define the signature kernel as the inner product of two signatures. So signature kernel or I should rather say the phi signature kernel indexed by phi is, so it's a map. So let's call it K phi. So this is a map from unparameterized paths. So let me, okay, so let me do a simplification for this part. Actually, I won't look at anything else than a path of bounded variation. Things can be extended to higher P's with the same sort of techniques, but let me focus entirely on bounded variation paths. And so C1, these are unparameterized path of bounded variations. I will not put the one here. We'll just do C like this. So the signature kernel can be defined as a function that takes in two unparameterized paths and that outputs a number. Okay, so this will take one equivalence class, another equivalence class, and will produce the inner product. So we know that the signature, I can remove the equivalence class because they're all the same. S of x, S of y, inner product in T phi of V. Okay? That's it. So that's the definition. Now, especially for practical computations, it will be useful to consider a slightly, the same version, but parameterized by time. Okay, so instead of working with unparameterized paths, I can work with paths. Okay, so I can define the equivalently. So K phi of x. Now it's actually a path. It's not an equivalence class. K y, and then I have other indices. So S comma T. So these are two time indices that define this kernel in this way. So this would be the signature of x from, let's suppose that x and y are 0, 1 to V. Then this will be signature of x between 0 and S, signature of y between 0 and T, inner product in T phi of V. Yeah, that's so. If there is no, if there is no indices, it means that it's really on equivalence classes without taking care of the interval. If there are some time indices, it means that I just look at the signature of x up to S and the signature of y up to T, and then I take their inner products. Right. So now we have this definition, and then so one identity, important identity. Let me do this. So lemma. So let me define this function. So let phi plus be another weighting function. So from n to r plus, that is defined as, so phi plus of k is equal to phi, so the original phi evaluated at one step up, phi k plus 1. Okay. Right. Then the following holds. Then what do you have? You have that k, so the signature kernel k phi of xy st is equal to phi of 0 plus the double integral, and this is not an iterated double integral, it's actually, you know, a classical double integral. So this is u between 0 and s. This is v between 0 and t. Of what? Of k phi plus xy uv, inner product dxu dyv, and this is the inner product in v. Okay. Right. Okay, so this is a relation that is satisfied. So, very important remark, this is not the differential equation, okay, because the left-hand side and the right-hand side are not the same. These are two different objects. So in principle, this is just a relation, the integral relation. So how would you prove this? It's a calculation, essentially. So this k, so okay, that means, so k phi xy st by definition is what? Is phi 0 plus the sum I equals 1 to infinity of phi I times the signature of x at level I between 0 and s, and the signature of y level I between 0 and t in the tensor I. But now this is what? This is phi 0 plus some I equals 1 to infinity. And then I have phi I, and then I can use the definition of the signature. The ith level of the signature can be re-expressed as the integral between 0 and s of the I minus 1, I minus first level of the signature between 0 and s dxs. And the other one is the integral between 0 and t of sy I minus 1 0 t dyt, inner product in V tensor I. Where here I have the product. Well, I guess this is the tensor product. Okay. Right, now what I can do is that, okay, I can swap sums and integrals because things decay very fast, right? So we have dominated convergence, we can swap things. So let me do that. So phi 0 plus, what do we have? We have the double integral. So you see here it's coming, so u, sorry. So this is u u 0 to s, just to be clear, v 0 to t. Okay, so then I have a sum I equals 1 to infinity phi I. Now let me do a trick, which essentially consists in saying that, you see, this is an inner product of two products. So this is a, this is a product, this is another product, and then I take the inner product of these products. Well, this can be split in the following way. So this you can write it in this way. So you have the signature of x 0u at level I minus 1, and then I take the inner product with the signature of y0v at level I minus 1. This is the product in V tensor I minus 1, the one before. And then I multiply this by the inner product of the individual increments. So this is the xu dyv in V. Okay, so what I've done here in this step is that I've split, use this, an algebraic computation that splits the inner products of two products as products of inner products. So, right, now, okay, so now let's use colors. Let's just change indices. So, so let me change the index. So I start from 0. So this becomes +1, and this becomes I and I. Okay, just a change of index. And now this part, well, what do I want? Sorry. Oops, no. Can I go backward? Yes. Good. This part is by definition just, the phi plus inner product of the signatures. This is with respect to phi plus, okay? And therefore, this is equal to k phi plus of xy uv, right? So yeah, so that's where it comes from. Right. So then, okay. So then, if you pick phi, so there is a a simple example. Now, if you pick like this, so for example, if phi of k is just a constant, let's put a constant equals to 1. Okay, then it means that I'm just taking sums of signatures without rescaling them. Well, then if phi is as a constant, phi plus is equal to phi. Right. So this differential equation, this integral relation becomes a differential equation. In this case, then k phi xy st is equal to 1 plus the integral of k phi xy t uv dxu dyv. Okay, and so this is 0, 0s, 0t, and then you can differentiate with respect to s and t on both sides, and there you get a PD, k phi xy ds et is equal to k phi xy st dxs dyt. Okay, so that's a PD. Right, and so then what happens is that, sorry?
I'll go up to time.
Is it? Okay, it's not until 1? Oh, okay. So it's just 1 hour after.
1 hour break now.
Yeah.
Ah, okay, okay. Okay, so yeah, so maybe I just give the last comment here is that you don't need to compute signatures to compute this kernel. You just evaluate the PD and you try to evaluate the PD and yeah. Okay, sorry. Yeah, I thought I had another hour. It's okay.
Okay, so let's thank